Right, everyone. This is the Exam 2 review for Fundamentals of Physics. I have about 10 questions that I've pulled together that I feel are some of the most important concepts for the second test and also probably some of the most missed problems on the second test. So I'm just going to run through them here. The first question is, if two objects are moved 4 times farther apart than they were, what happens to the gravitational force between them? So this question is going to be all about proportionalities. Anytime that you are asking about what happens to one value when another thing changes, you know that we're looking at our proportionality relationships. So here, it's talking about objects being moved further apart than they were. So that's asking about when you change the distance, what happens to the gravitational force? So I want to go to the equation sheet and look for an equation that has gravitational force and distance so that I can discover the relationship between the two. So I would go to my equation sheet, and of course I would see Newton's universal law of gravitation, which says that the gravitational force is equal to the gravitational constant times the two masses divided by the distance squared. Now, I'm not given any specific numbers for this problem. I'm not given specific masses or specific distances, so I don't even need to worry about what mass 1 and mass 2 are. All I'm concerned with is what is the relationship between force and distance. And here we can see gravitational force is on top of a fraction. If it's by itself, remember we can always put it over 1. And then the distance is in the bottom of the fraction, so we can tell that the opposite thing is going to happen to them. If the distance increases, then the gravitational force is going to decrease. But it's not going to go up and down by the same amount because of the square in the problem or in the equation. Hold on 1 second. All right, sorry about that. Every time I start a recording, my dogs like to get into a fight right next to me, and it's very distracting. So, all right, so we know that the opposite thing happens, or the inverse thing happens to gravitational force and distance. So if the distance increases, then the gravitational force will decrease. If the distance decreases, then the gravitational force will increase. But because of the square in the equation, they're not going to go up and down by the same amount. They're going to go up and down by an exponential amount. So if two objects are moved 4 times further apart than before, that means that the distance has increased by a factor of 4, and the gravitational force will decrease by a factor of 4 squared, or 16. So if this goes up by 4, this goes down by 4 squared, or 16. All right, the next part of the question asks, what happens if one mass increases by a factor of 4? So again, this is asking about what happens to one value when another changes. And in this case, the two values that we're concerned with are one of the masses, doesn't matter which one, and the gravitational force. So again, we don't care what any of these other values are. All that we care about is the relationship between the gravitational force and the mass. And you can see pretty easily that the mass is on top of the fraction. And again, gravitational force is by itself, so it can be put over 1, and we'll consider it on top of a fraction as well. So because they're both on top of the fraction on either side of the equal sign, that means that the relationship is directly proportional. So directly proportional means that as one value increases, the other value will increase as well, and by the same amount. And then the same thing goes if one value decreases, the other value decreases as well, and they decrease by the same amount. So if one mass increases by a factor of 4, then the gravitational force will also increase by a factor of 4. The reason I put this one on here is not only to re-emphasize the very important concept of proportionalities, but you also want to make sure that you read the problem carefully. So often, people just get into their heads that we always ask about gravitational force and distance because we, talk a lot about the inverse square law and how that's such an important relationship. But we can ask about the masses as well. So just be sure to read the problem carefully to figure out which two values you're comparing. All right, second question. What is the pressure on a table that holds 10 kilograms over an area of 0.5 meters squared? So first thing I want to do is identify what I'm given in the problem and what I'm solving for. So if I write down my list of variables, you can see that pressure is my question mark. That's what I'm solving for. The mass is 10 kilograms, and the area is 0.5 meters squared. So pressure equals force over area. If you go to your equation sheet and look for the pressure equation, you'll see that pressure equals force over area. For this problem, we are not given the force directly. We are given the area, so we're all set with that. But we can see that the force isn't directly given in the problem. So we need to figure out a way to be able to find the force with the information that we're given. And in this case, if you think about what the question says, it says, what's the pressure on a table that holds 10 kilograms? So you basically have 10 kilograms of mass sitting on top of a table. And for that, the force is going to be the weight. Remember, force or weight is just a specific type of force that is that an object has downward on another surface due to its mass. So if there's 10 kilograms sitting on a table, then the weight on top of that table is the force downward on that table. So weight is equal to mass times gravity. So we can rewrite this equation as pressure equals mass times gravity divided by the area. And then it becomes simple plug and chug. My mass is 10, gravity is a constant 9.8 divided by 0.5, and I end up with a pressure of 196 pascals. Now remember that on your equation sheet, we give you all of your units. So even if you don't remember the units for pressure, you could always go to the pressure problem. And right next to it, you have the symbol, and that's what is in the equation. That's the P. But then the unit is in this third column here, and you can see it's PA or pascals. All right, next is an actual calculation problem using the gravitational force equation. This equation is probably the most daunting and longest equation that we have, but if you take it step by step, it's really not any more difficult than any of the other equations that we've had in this class. So let's take it step by step. We want to know the gravitational force between Mars and Earth, given the masses of both Mars and Earth and the distance between them. So we know gravitational force, and the magnitude of gravitational force is just the amount of gravitational force. So write out your equation, and this is definitely one I recommend doing on your scrap paper, and plug in your values. Don't forget that gravitational constant is 6.67 times 10 to the negative 11. That value is always going to be there when you do this type of calculation. And then plug in your masses. The mass of Mars, 6.39 times 10 to the 21st, times the mass of the Earth, 5.97 times 10 to the 24, divided by 5.46 times 10 to the 10th squared. Don't forget that square. That is by far the biggest mistake made in this calculation, is forgetting to square the distance in the bottom of the fraction. So I like to do that first or second by leaving the gravitational constant out in front and reducing my fraction down to just one number divided by another number. So the two masses multiplied together ended up giving us 3.81 times 10 to the 46. And then squaring the distance gives us 2.98 times 10 to the 21. Divide those two things to just give us a number. You end up with 1.28 times 10 to the 25th times the gravitational constant, and we should end up with a gravitational force between of 8.53 times 10 to the 14. Now, a good check on this is just to is to look at your answer and make sure that it makes sense. And that's really a good check for any question. One of the best questions that you can ask in physics is, I got this answer, does it make sense to me in the real world? Remember, physics is the math of the real world. So obviously there's going to be a large gravitational force between Mars and the Earth because they're such massive objects. So if you got a gravitational force in this equation of 8.53 times 10 to the negative 14, then maybe that wouldn't make a whole lot of sense because that was less than even what we calculated as the gravitational force between two people on Earth. So you know in your head that you're going to have a large number for this. Know that if you have small masses, you're going to have a small number for that. All right. Will a rock with a mass of 200 grams and a volume of 400 centimeters cubed sink or float in fresh water? So if you see a question that wants you to identify if an object's going to sink or float, then you are really asking about the density, because we know that the density of an object determines if it will sink or float. If the density of the object is greater than the density of the liquid that it's floating in, then it will sink. And if it's less than the density of the liquid that it's floating in, then it will float, or the liquid that it's submerged in, then it will float. And if it's the same density as the liquid that it's submerged in, then it will be able to stay at whatever depth you put it at, and it won't float and it won't sink. It will stay suspended underneath the surface. So our density equation, we'll go down and look for our density title here, and you'll see rho equals mass over volume, rho being the symbol for density. So we end up with 200 grams divided by 400 centimeters cubed, and 200 divided by 400 gives me 0.5, and my units are grams per centimeters cubed. Remember that density is one of those is our only one so far anyway that can have different units depending on how it's given in the problem. So if you go to your unit on the density, your unit column on the equation sheet for the density equation, you'll see that the density can be in either kilograms per meters cubed or grams per centimeters cubed. And that will depend on if the mass is given in grams or kilograms, or if the volume is given in meters cubed or centimeters cubed. I recommend doing it just like this, actually plugging in the units into the equation so that it completely eliminates the risk of getting it wrong. If you just plug in those values, then you already have your units right there solved for you. So we ended up with 0.5 grams per centimeters cubed. So what we want to compare this to is the density of water. And the density of water is pretty easy to remember, but if you don't remember, we give it to you on your equation sheet. It is just 1 gram per cubic centimeter. So since this rock has a density that is less than 1 gram per centimeters cubed, then it will float in fresh water. All right, time for a concept question as opposed to a calculation question. So if a neutral carbon atom gains an electron, what does it become? Now, in all of these, I want you to think about, when you're reading the question, what protons, neutrons, and electrons contribute to an atom. So keep in mind that electrons have a lot of charge, but very little mass. So electrons have a negative charge, so they contribute to the net charge of an atom, but they do not contribute a whole lot to the mass because they're so much smaller than the other two subatomic particles. Protons are relatively heavy, and they have a positive charge, and they are located in the nucleus. Neutrons are neutral. They have zero charge, but they do contribute a lot to the mass of an atom because they're about the same size as a proton. So protons and neutrons contribute almost entirely to the whole mass of an atom. So if we take a neutral carbon atom and give it an electron, what does it become? That means that it's not gaining a lot of mass, but it is gaining some negative charge. And if it was originally neutral, that means that it had the same number of protons and electrons before, because protons have a fundamental charge of +1, electrons have a fundamental charge of -1. So when you have the same number of protons and electrons, you have a neutral atom. If you gain one more electron, that means you're gaining a negative charge, and you end up with a negative carbon ion. It is still carbon, but it is just a charged atom now. It's a carbon atom with a net charge called an ion. The next question, if it starts again at neutral and loses an electron, what does it become? Here, we again started at neutral, same number of protons and electrons. But if you lose an electron, that means that now you have more protons than electrons, which means you have more positive charge than negative charge, and you end up with a positive carbon ion. Again, still carbon, just carbon with a net charge, and this time it's positive. And in order to become an ion, you only gain or lose electrons. You don't gain or lose protons, only gain or lose electrons. All right, so the third example here, if it gains or loses a neutron, what does it become? Remember that neutrons have a neutral charge, so they don't contribute to the net charge of an atom. If you gain or lose a neutron, that doesn't affect the charge of the atom at all. The only thing that it does affect is the mass. And if you gain or lose a neutron, it changes the mass then from what's listed on the periodic table, and it becomes an isotope of whatever atom it is. So in this case, if we started with a neutral carbon atom and gained or lost a neutron, then we end up with an isotope of carbon, which is just an atom of carbon that has a different mass than what was originally listed on the periodic table. All right, and then finally, if it gains a proton, what does it become? And protons, if you remember, protons are the thing that determines what type of atom it is. So if you gain or lose a proton, it actually becomes a whole new element. So if a carbon atom gains a proton, it actually becomes nitrogen. All right, another concept question, which might look like a calculation when you're reading through it, but because it's asking for speeds. But again, these are just things that you'll want to memorize. These are numbers that you'll want to memorize for the test tomorrow. So the first one says, what speed does an object need to maintain to stay in orbit around the Earth? And the answer for that is 8,000 meters per second. What speed does an object need to obtain in order to escape the gravitational pull of the Earth? And the answer for that is 11,200 meters per second. And then finally, the speed that an object needs in order to escape the gravitational pull of the solar system or the sun. Remember, the sun contains over 99% of the mass of the solar system, so the escape speed for the solar system is pretty much the escape speed of the sun, and that speed is 42,500 meters per second. So again, just be careful to read the problem carefully and figure out which one we are asking for. The smallest one is obviously going to be to maintain orbit. The second smallest one is going to be to escape the gravitational pull of the Earth, and then the largest one would be to escape the gravitational pull of the sun. In between these numbers, you'll find slightly different paths of the objects. So anywhere in between 8,000 and 11,200 meters per second, the object is going to stay in orbit around Earth, but the closer it gets to 11,200, the more elliptical that orbit will be. So at 11,100, that object is going to think, oh, wow, I'm really close. I'm going to be able to pull away from the gravitational pull of the Earth, but then it gets sucked back in because it hasn't actually reached the escape speed of Earth. So anything between 8,000 and 11,200 will still orbit Earth. And then anything in between 11,200 and 42,500 is going to orbit the sun. This allows us to get away from Earth, and this allows us to get away from the sun. So anything in between, it's going to pull away from Earth, but then it's going to get sucked back into orbit around the sun. It's not going to be able to escape that. So anything in between 11,200 and 42,500 is going to orbit the sun. And again, the closer it gets to this maximum, this escape speed here, the closer it gets to 42,500, the more elliptical that orbit will be around the sun. All right, this question has to do with the Pascal's principle. The piston on the left side of a closed hydraulic system has an area of 5 meters squared, and the piston on the right side has an area of 10 meters squared. If a force of 200 newtons pushes down on the left piston, what force will the right piston push up? So anytime you see these words, closed hydraulic system, you're going to want to immediately be directed to Pascal's principle on your equation sheet. And Pascal's principle says that the pressure on one side of a closed hydraulic system is equal to the pressure on the other side. And since pressure is equal to force over area, we can rewrite it in this way. Force over area on the first side equals the force over area on the second side. So you just want to be careful when you plug in your values to make sure that you keep everything that's on the left side of the hydraulic system on the left side of the equal sign, and everything on the right side of the hydraulic system on the right side of the equal sign. So here we have 200 newtons on the right side, or sorry, on the left side, and over an area of 5 meters squared. The area on the right piston is 10, and we want to figure out what the force will be upward on that right piston. So if we increase the amount of area, we should know that this force is going to have to increase as well, because the ratio of force to area on one side has to equal the ratio of force to area on the other side. But we can cross multiply to check this. 200 times 10 equals 2,000. And then that equals 5 times the second force, or the force on the right side. To solve for F2, we need to divide both sides by 5, and you end up with 2,000 divided by 5 equals 400 newtons. And if you bring this back into check, you can see 200 divided by 5 is equal to 40, and 400 divided by 10 is also equal to 40. So a good check is to go back and plug that into the equation and make sure that the ratio is equal to each other. All right, a rock is thrown horizontally off a cliff with an initial vertical speed of 0 and an initial horizontal speed of 8 meters per second. If the rock encounters no air resistance and remains in the air, what will its horizontal speed be after a time of 5 seconds? So this is asking about projectile motion. And remember that the definition of a projectile states that an object as a projectile has to have a constant horizontal velocity and an accelerating vertical velocity. Remember that forces are the only things that can cause accelerations, and the only force acting on a projectile is gravity. So since gravity is always a vertical force or an up and down force, then that's the only direction that the object can accelerate. There are no forces acting in the horizontal direction, so the horizontal speed is going to remain the same. So this first part here, when it asks about what is its horizontal speed after a time of 5 seconds, those key words right there tell me that this isn't going to be a calculation problem, even though it might look like it. If the horizontal speed started at 8 meters per second, it's going to end up at 8 meters per second. The horizontal speed of a projectile is constant. After 5 seconds, after 10 seconds, after 1,000 seconds, as long as it's still in the air and we're neglecting air resistance, then that horizontal velocity is going to remain the same. Where it does become a calculation is if we ask you what its vertical speed will be. its vertical speed is changing because gravity is pulling it down. So every single second, it's getting faster and faster because of the acceleration of gravity. So this equation really stems from our acceleration equation from the first test and the very first day of class. And this is the one that you'll be given on your equation sheet. So you can memorize velocity equals gravity times time for vertical speed, which is what we end up with here, or you can use the actual acceleration equation, whichever one you're more comfortable with. This right here is the one that you'll be given on the equation sheet. But for a projectile, we can rewrite this because the initial speed was 0. You can see initial speed is 0. The final velocity is what we're solving for. The time is what we're given. We know that's 5 seconds. And the acceleration, because this object is essentially in free fall, a projectile is in free fall, then we can replace that a with g. We can replace it with 9.8. So v final minus 0 is just v final. V final over t equals g. If we solve that for the velocity by multiplying both sides by time, then we end up with velocity equals gravity times time. So for vertical motion of a projectile or vertical speed of a projectile, you just have to multiply however long it's falling by gravity. And in this case, we end up with 9.8 times 5, and the final velocity that that projectile ends up at after 5 seconds is 49 meters per second. All right, another projectile question. This time we're concerned with launch angles and ranges. So the launch angle is exactly as it sounds, the angle at which the object is launched. And the range is the distance, the horizontal distance on the ground from where the object was launched to where it lands. So in this case, we ask a projectile is launched at an angle of 33 degrees and travels a horizontal range of 100 meters. If we neglect air resistance, again, we always neglect air resistance in this class. Physicists like to do that because it makes our lives easier. And we want to know what other launch angle will achieve a range of 100 meters. So here you have to remember the concept of complementary angles. Any two complementary angles, which are two angles that add up to 90 degrees, will travel the same range. So any two angles that add up to 90 degrees will achieve the same horizontal range. So since we were given the first angle is 33 degrees, we need to know what added to 33 will give us 90. And a good way of doing that is 90 minus 33 equals 57 degrees. So 57 degrees, if 33 degrees gave us a horizontal range of 100 meters, then 57 degrees will also give us a horizontal range of 100 meters. So 90 minus any angle that we give you will give you the complement to that angle, which will achieve the same range. All right, what volume of water will be displaced when an object of mass of 3 kilograms and a volume of 8 cubic meters is completely submerged? Here, this has to do with the displacement principle. The displacement principle says that whenever an object is completely submerged, the volume of water displaced is equal to the volume of water, or the volume of the object. So if the volume of this object was 8 cubic meters, then the amount of water that's displaced is also 8 cubic meters. This mass in here is just given as extra information. You don't have to worry about the mass. Remember, just if you think about putting something inside of just say you have a cup of water, say you have a small object. If you put that small object into the water, you know that that water level is going to rise. The amount that it rises is the amount of space that that object that you put inside of the cup takes up. So that volume of the object has just been displaced by the water by that same volume. So This might look, again, like a calculation problem. If we give something like this, it's very easy to think maybe this is a density problem because we give you mass and volume. But remember that if you see the words displaced, then think about the displacement principle. All right, those were my 10 questions. And finally, I just want to finish this up with a couple of definitions that I think will be important to know for the test. Here we have the first one is the atomic number. The atomic number is the number of protons in an atom. The atomic number determines what element, what type of atom this is, what element it is. Remember the numbers that count up, starting with hydrogen at 1 and helium at 2. On the periodic table, that is the atomic number, and that tells us how many protons are in the nucleus of that atom. Noble gases. Noble gases are a full column of the periodic table. If you're looking right at the periodic table, it is all the way over to the right side. Starts with helium and then goes down. It has like neon and krypton and all that, xenon, I believe, all down in that column on the right side of the periodic table. These are special gases because their outer shells are completely full of electrons. And that is all that an atom really wants. It's always trying to get its outer shell completely full. So if an atom already has its outer shell completely full of electrons, then it's achieved what it needs in life, and it doesn't need to borrow, steal, get rid of, or do anything to get its outer shell completely full. So because of that, it will not react with any other elements. You will never see a compound, a natural compound with any of the noble gases because it can't combine with any other elements. All right, weightlessness. This is like the astronaut video that we showed in class. Weightlessness is not a lack of weight, but it is simply a sensation that is felt due to a lack of support force. An example of someone feeling weightless would be when someone is in free fall. So in free fall, gravity is the only thing that's acting on you. Remember that the only reason we feel gravity at all is because we have a support force. If there is an opposing force, then we can feel gravity. But if there's no opposing force, then we don't really feel gravity and we get the sensation of being weightless. So weightlessness is a feeling that is felt due to the lack of a support force. And then we already kind of went over these last two here, but isotopes and ions, these are two definitions that are pretty understandably easy to get mixed up. An isotope is an atom that has a different mass than is listed on the periodic table due to having a different number of protons and neutrons. And then lastly, ions are atoms that have a net charge because they have a different number of protons and electrons. Protons have a positive charge, electrons have a negative charge. If they have the same number of protons and electrons, then those charges cancel each other out. But if you have an unequal number of protons and electrons, you end up with an ion, and that ion can be either negative or positive depending on if you have gained or lost electrons. All right, guys, that is the end of my review. Thank you for listening.